Welcome everyone to the week 5 tutorial session of Galois theory MA70. Today we will discuss questions related to week 5 lectures. So let's begin. Let L over K be a simple algebraic field extension with primitive element X belongs to, so it was written K in the sheet. It's just a typo. You can change it to L because it does not make sense otherwise, or maybe then it will be just trivial. So the primitive element is X for this simple extension. So what is a simple extension?
Only a field with associating a single element.
Exactly. So this extension, very good. So this extension means, so if L is a field extension over K, is said to be simple if it can be written as with just one element, attaching one element. So it's like L is equal to Kx. So primitive element is corresponding to that only. So this is the extension. So sometimes I write a small x capital X. It does not say that this is algebraic or something like that. Simple means it's just you can write the field as Kx where X is some element of L. Okay, it just mean that. So for example, if you say, let's say K capital X, so capital X, this is a variable means it's a indeterminate. Okay, so if that is the case, then this is also a simple extension of K, because this is a field. We have used this small bracket. That means we are allowing rational, like for example fx by gx, where gx is non-zero. We are allowing that. So this is a field. We are adding inverses, right? So this is also a simple
Ma'am,
extension.
actually, K open bracket X is a field containing the third bracket of X. Actually, it is a quotient field of that given field, the given K third bracket X
Yeah,
quotient.
yeah, exactly. So it's like, so what do we write in general? What is this? This is K sub algebra, smallest K sub algebra, containing, so not even that. So even I can write, okay, that's fine, containing X and, yeah, containing X. I already said this has K. uh, have I right? Oh, okay. So basically I should write like this, and then if you want a field, then you can write, sorry, this is smallest uh, field extension of K. Yeah, maybe smallest field containing X and K. Maybe you can write like this. So it's from these notations itself. So this is, as you said, this is a quotient field of Kx. So we sometimes write, maybe I guess this, something like that. So this means quotient field of Kx. So you are allowing inverses. So, so I just mean that if it is given to be simple, that does not mean this is algebraic. That you should always remember. But now it is given that this is algebraic. So can you conclude something? So L is given to be something like Kx, where x is the primitive element, uh, a primitive element, and this is given to be algebraic. Can you tell me what can you conclude with these two conditions in terms of? Okay, so I'm saying, do you understand that this implies that this is a finite extension? So I'm claiming this. Can someone explain? if it is simple plus algebraic. So as you know that only algebraic does not mean that this is a finite extension, because you can take for example okay, so maybe you can take this C over Q, right? So you know that every polynomial has a root in this complex set from the fundamental theorem of algebra. So yeah, so this is algebraic, but we know that this is not finite. So there exists some infinite field extension which are not which are algebraic, right? So the point is, if this is simple, then it becomes finite extension also. Or maybe if you want more examples, I can give, for example, Q.
No, so if we consider x, then some power of x would be in K, right? So the vector space
Mm-hmm.
dimensions
Just
that.
some power,
Therefore,
or
it has to be finite.
sorry.
Some power of x
Hmm.
will be in K
How is it? How exactly will you say that?
because I can always say that the
Mm-hmm.
root will be some x power n minus something, right?
Uh, yeah, right.
So the so in a sense,
So
if x
maybe.
is an element
Mm-hmm.
in L,
Right, right.
and I mean it's the simplest field extension based on x,
Hmm.
then since so x power n is in K, so therefore the vector space of L will have that dimension n, which
Okay.
is a finite number.
Exactly. So the point is you can just directly say, and other thing you were saying like x raised to power n. So you take this minimal polynomial of
Huh.
x, yeah. Then you know that directly from this epsilon thing. So degree of this is same as so this map you remember. So you have kx. This is isomorphic to as k algebra k capital X by mu xk, right? So you know that this degree of mu xk is same as the dimension of kx over k. So that is exactly your dimension of, because this is L. So you know that this is finite degree because you have said that this is algebraic. So kernel is non-zero. That means there exists some polynomial in the kernel. That means it will have some minimal polynomial, and this will have degree finite. So this is some finite number. So let's say less than infinity sometimes. So this is a finite number. Okay, because you are just attaching one element, and you can always get a so you can always do this and get this dimension to be finite. Okay, so yeah, and as you were saying, this the other thing. So you have some polynomial, let's say mu x or any polynomial. There, this is algebraic, so there will exist a polynomial. Let's say a n minus one x raised to power n minus one plus up to and so on. A0 equals to 0. Yeah, then as you said, we can write this to be in terms of other things if these are non-zero. At least we know that this is 1, so these could be 0. Anything, we don't care. Some power could be 0, or if this is like not integral domain, but that is not the case. We are always in a field right now. So you will have something like that. And now so x raised to power n, yeah, so x raised to power n will be equal to this, but so what you can say at least that so maybe not from this, at least the other way is to say always in the sense that if you take 1 x x square up to and so on x raised to power n minus 1, then you know that this mu xk has degree n. Then this set x raised to power n, this set will be linearly dependent. because you know that this, as I wrote earlier, you have this kind of relation between these powers, right? So it will stop somewhere, so degree is finite. That is the other way, if you want to say. So basically this is linearly dependent, and if I have just taken minimal polynomial, then we cannot go degree down, so this will be linearly independent. So this is linearly independent, that's, and this is a basis also. So you have, as a vector space dimension, you have this to be the dimension to be equal to n, exactly from this. So this other explanation. Okay. Any doubt in this? So this is some kind of thing to remember, or maybe observe that if a field extension is simple plus algebraic, then it will be a finite extension. Okay. So, and if it is just one of them, then we cannot guarantee that. For example, for the case of simple, if it is simple, you can just take this indeterminate thing, then it will not be a finite extension. Okay. Second thing, if it is algebraic, then again we can take this example, C over Q, right? And there is one more example if you want to consider, which I was writing earlier. You just take all the primes, which you know that these are infinite. Okay, so over Q, that is also of infinite dimension, because you are not limiting it. Okay, even second example will also prove that this is an infinite extension. Is that okay, this part? I'll continue with the question now. Okay, so what it says, let E be an intermediate subfield of L over K, and mu x comma E is equal to this, belongs to Ex. So what does this say? So you take some E in between this K and L, okay, and minimal polynomial of X in the base field E is given to be b0 plus b1x plus up to and so on bn minus 1 x raised to power n minus 1 plus x raised to power n. I hope n is there. Yeah, m. Okay. You have m. Okay. So this belongs to Ax. This is the minimal polynomial of x in Ex, or in E over E maybe. Now they are asking show that E is same as K b0 b1 up to and so on bn minus 1. So they are saying it's just K with these coefficients. So E is equal to K with these coefficients. Is the question clear? Is the question clear?
Question, please. You have not repeat the question. Please show the question.
Okay. So question says, let L over K be a simple algebraic field extension with primitive element x belongs to K. That means L is equal to Kx. Okay, L is equal to Kx, first thing. Second thing, you consider any this subfield of L containing K, and take this mu xe. Mu xe is always a notation for minimal polynomial. So minimal polynomial is given to be minimal polynomial of x in E. Oh, so now base field is E. So you are talking about this part. So mu x comma E. So E means the coefficients are coming from E.
Yes, yes.
So Bm minus 1 x raised to power m minus 1 plus x raised to power m. This belongs to Ex. This is the minimal polynomial of x in E over E. Now show that this E is exactly equal to k with attaching these elements. So we have to show this, which,
Okay.
yeah, which does not seem clear, of course. I don't see directly at least. So here we know that L is given to be kx. Okay. Okay. So kx plus algebraic. So as I said, algebraic is needed. Now, okay, let's see. So how shall we proceed? There is a hint also. So let's do one thing. So let E dash is equal to k b0 b1 up to and so on bm minus 1. Right? Assume that we just take this, define E dash to be k b0 to bm minus 1. Now what do we know? So what can you say, what can you tell me? So there is this relation k and this. So somewhere you have E dash and E. So where should I write E dash and E? So what is the obvious containment? So I want to write at these places E and E dash. So where should I write, I'm asking. What containment is obvious?
Ma'am, 1 minute, I'm not very sure.
E containing it is.
Uh, E is contained in E dash, and what were you saying? Abhiram?
I'm not really sure with the notation of k of b0, b1 up to bm minus 1. What does that exactly mean?
Okay, okay. So this means field, subfield of, or if you want, k subfield of L containing b0 b1 up to and so on bm minus 1. So it's like what we were doing earlier. So kx is like, so even you can write a smallest k subfield of L containing b0 to bm minus 1 elements. So it's like what kx denotes? Kx denotes smallest k subfield.
But okay, let me take the example of the fourth root of 2.
Fourth
Then,
root of 2, okay.
so if I take k, then L will be basically everything that contains up to the fourth root of 2. Matlab the field extension of, I'm taking with respect to rational numbers.
Mm-hmm.
So let my base field k be q.
Okay.
And now my L will be q of fourth root of 2.
Fourth root of 2 in just, should I write all the fourth roots, or so it's
I mean, wouldn't it be the same thing?
no, why? So for example,
Because the simplest extension would contain the fourth root, the second root, and 1 itself, right?
fourth root of 2, okay, and you're saying this. Okay, let's see. What does it mean to have fourth root of 2? That means what are all the roots it will have? So it's like square root of 2 and x square plus square root of 2. So here you will get iota also. So it's not all. So the roots of, so as in terms of splitting field, if you understand. So this q, if you just attach this, or for example I just take third root, that will be better to explain at least. So if you take, for example, cube root of, let's say, just 1 only, okay, So or maybe, okay, let's take 2 to clear the confusion. So what will be the roots? So you have this root. If you just attach this, this is still not a splitting field. Splitting field means it contains all the roots of this equation. Like this equation splits in linear factors. That is
So
exactly the
you're
meaning.
saying we should consider
Yeah, there are
the
more.
root 2
So
of the cube root of 2 with omega and
yeah,
omega
yeah,
squared.
exactly. So so if you want to consider, so as you when you said I just take cube root of 2, then I was asking which one I should take. So that's what I was
So
asking.
coming back to this one, now
Yeah.
if I say, uh,
So
so with the
let's
fourth root
take.
of 2 itself,
So you just take simple example. Let's say this and this, and just attaching two elements.
okay.
So what does this mean? You first take this and then even take this. You can even understand
No,
in this
that
sense.
is fine. So now if I'm taking e to be, say, q of root 3.
Cube root 3. Okay.
No, 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 no. Just root 3.
Oh, sorry. Q root 3, you mean?
Sorry.
Yeah.
Yeah, q root 3. So then the minimal polynomial will be x square minus 3 will be equal to 0.
Yeah. Yes.
So then the extension, like what we're telling is that it should be e should be equal to k of 1 comma 3.
1 second. So you are saying e to be 1 comma
K
3.
of 1 comma 3. That's what you wrote, right?
Okay, so let me explain in this sense. Okay, I got your point. What we okay, so let's take this example itself. So okay, this cube root of 2. Let's take this only. Sorry, not cube root of 2. So you have this, and now as I was writing, so you have this. So it will split in, so what is the formula? So this here you will have minus, here you will have plus, multiplication of, I think, yeah, cube root of 2x, was it? I don't remember. What is the formula? X cube minus y cube.
X minus y into x square plus xy plus y square.
Yeah, exactly. Very good. Thank you. So you have y square. So you have cube root of 2 square, and you will have x into y. That means this only. So you can write x cube minus cube root of 2 cube equals to 0, and I use this formula. So you get this. Right. Now, so so it has roots. So this polynomial will have okay, this will split in so you have this omega is cube root of unity. Non-trivial cube root of unity means, so cube root of unity, it's like x minus 1 x
Got it. This
square.
will be minus 1 plus
Yeah.
plus minus root 3i by 2.
Yeah, so omega, and so the roots of x cube minus 1 is like 1, and there are two roots from here. So we write in the notation omega, which satisfies omega square plus, so which satisfies this condition, and the other root will be like 1 minus omega, not 1 minus omega, sorry. So yeah, so omega square will be minus omega minus 1, and yeah, omega square will be there, I think.
Yeah, the other one will be omega square.
The other one will be omega square. Okay, so I mean there are other roots. Okay, so the collection of roots are more than that. So maybe it will split like this. Yeah, omega square. Maybe whatever it is, something here. So it will be, omega will be there. Okay, so for example, in our situation, let's say q is your base, which is k. E is some in between, let's say that is q cube root of 2, and let's say the next one is L, which contains all the roots. So that means you have omega also, cube root of unity also. So in the, so this extension, so when you take so you have cube root of 2, and the minimal polynomial of this, So L over K. So minimal polynomial of cube root of 2 over K will be what? X cube minus 2, right? Because it cannot split. So K's are cube. So in Q, x cube minus 2 will not split. So it will be the minimal polynomial of cube root of 2 in Q over Q. Now when you go in some bigger extension, so you allow something more. So you say now you are in not in Q, you are in Q attached with this cube root of 2, then the minimal polynomial will be what? Because it will split, because this condition does not require any other element. You just if you have cube root of 2, then you have all the coefficients, right? So that means its minimal polynomial will be this. Okay, so its minimal polynomial is this. So in our situation, and now if you attach L, so L could be bigger than that.
It will be x minus cube root of 2 only, no?
Sorry?
This will be x minus cube root of 2 only. The minimal polynomial of cube root of 2 over q of cube root of 2.
Oh,
In the
okay,
last
okay,
line.
okay. Right. Yeah. You are right. So x minus cube root of 2. Exactly.
But ma'am, E is a field. It contains cube root of 2.
Sorry, come again. Or maybe we can do this also. This is better maybe. Yeah, what you were saying, Anjani?
Ma'am, E is a field and x minus cube root of 2 is a 1-degree polynomial, and
Yeah.
it also contains the
Yeah.
So it is
You will get minimal polynomial of degree 1. That means but the element itself is in the field. So let me modify this. So I have used omega also. Now for this, so with this it makes in so in our situation this is a better example. You take cube root of 2 omega. You are trying to find this minimal polynomial of cube root of 2 omega in over q. Then you have this minimal polynomial, because this will appear here only. Okay, now when you try to find the minimal polynomial in q cube root of 2, then you will get this. Is that okay now? So I have modified cube root of 2 omega because the root exists here in this part. So this cube root of 2, so this part will have the root cube root of 2 omega. One root is this.
And our claim is that
So
E should be
so L need not be a splitting field firstly. So in this situation, okay, we have omega because I have to increase to something. So maybe let's say if I want, I can just give root 5. Okay, then still this polynomial will not split in L. That is also fine. Okay, because this is bigger, but we are not saying that L is the splitting field of some polynomial. We are not saying that. So in our situation, what it is given, so in our situation it says that you take, okay, so our question is, there is this situation, you consider some intermediate field E in between K and L, and where L is Kx, and if minimal polynomial of x, so this primitive element x, minimal polynomial of x over E, now in this field, so like for example this one, this is given to be something like some polynomial b m minus 1 x raised to power m minus 1 plus x raised to power m. So this is in Ex. The coefficients are coming from Ex, like in this example. So this is your E, this is your K. Okay, so so this says, so if this is the case, then E will turn out to be exactly K attaching these BIs. So in terms of field, it just mean you are having B0 up to and so on Bm minus 1 inverse of that, just that smallest subfield containing elements of K and B0 to Bm minus 1, just mean that smallest subfield of L, K subfield of X if you want, right? Sorry, subfield of L containing B0, B1, Bm minus. Okay, so whatever you need, you just put it in this field. That just mean that like you are having X, Y, whatever it is, then you just allow inverses also. So then it will become a field. So it just mean that. So basically the question is saying if L is algebraic plus simple, then the primitive element which you have used, then any intermediate field of between K and L, any intermediate field will be can be obtained just by getting the minimal polynomial of that primitive element in that intermediate field. So just say that all the intermediate fields are coming from the minimal polynomial. This is the sense of this question. So there are no other intermediate fields. So it's a very strong condition, because you cannot always even write all the intermediate fields. So for example, if you take this, okay, as I was taking all the primes, let's say. So you have something like that, and you have Q. Then what are all the intermediate fields? You can have Q cube root of 2. You can have Q cube root of 3 plus cube root of 5. You don't know if this is equal to something else. And there could be, here there are infinite of course, but there could be anything like attach 2 elements, attach 3 elements. You take all the combinations. You can take twice of root 5, right? You can have so many. So this situation, this condition is stronger in the sense that you can you can find all the subfields just by knowing the minimal polynomial of so what are okay, I'll explain more. So what are minimal polynomials you can have? So here you are using E, but I'll explain. It's just not just E. You can just find it out just using K. Okay, so I'll just go the solution, and then maybe you can
So
understand.
then we should have E dash will be contained in E. That should be our.
Yeah, exactly. So as we started, yeah, that was something you can say trivial, obvious in the sense that you have K. So what we have assumed, let E dash is equal to K B0 B1 up to and so on Bm minus 1. Okay, so now you know that so you have K, you have L, so there are two things in between, E and E dash. So what I was saying, yeah, so E dash will be contained in E. That is obvious. Why? Because mu x comma E, so basically, okay, so here in this situation, you have given that b0 plus b1x up to and so on. This belongs to ex. So this minimal polynomial itself means that these coefficients bm minus 1 belongs to E, because this minimal polynomial, whatever coefficients you have, these are coming from E. So the coefficients are coming from E, so you have this situation, and already you know K is there. So K is a subset of E. So this implies from these two conditions, it will at least have the smallest field containing these two things, right? That is the definition. So this will contain so yeah, this will K B0 to Bm minus 1 is contained in E, and that is exactly your E dash. Yeah, is that clear why this is the containment?
Yeah, ma'am.
Okay. So it just E contains K, E contains these BIs, so it will contain E dash, because E dash is the smallest subfield of L containing K and B0, these BIs, right? So we have this situation. Now, okay, so you have Lx, sorry, not Lx, you have Kx is equal to L. So this implies, can you also say, if you just have x with E dash, then it will also be equal to L, and similarly this. Is that okay? Because you know that this is the containment. So this implies, so for, let's say you have, okay, yeah, that is better if I write like this. So you just take smallest subfields containing x everywhere. So the containment will be like this. And that is what L, x is itself x is an element of L, so it's just L. And what is this? This is kx itself, from this definition of simple, right? So kx, so these are same, so E dash x is equal to Ex is equal to L. So all these things has to be equal, right? This statement is clear. So we have, maybe let's say first, second, okay. So we have two containments. So firstly, K is contained in E dash is contained in E, and E is contained in L, and this other thing, right? Now third thing is, so I'm claiming that mu of x in E, which you already know. What is this? P0 plus P1x plus up to and so on Bm minus 1 x raised to power m minus 1 plus x raised to power n. So what can you say about x comma E dash?
It'll be the same polynomial.
Exactly, it will be the same polynomial. Why? Maybe one explanation if you can give.
Because you can't have a simpler polynomial. Like, at least the degree has to be the same thing, and all these coefficients are contained within it.
Exactly.
So it'll have to be the same thing. Like, let's assume there is a smaller polynomial, and because E dash is contained within E, this would have to mean that there is a simpler polynomial.
Right. So yeah, exactly. So you have E dash is contained in E, and E dash is okay. So E dash is contained in E. So what can you say about let's say, so if you are looking for the, so these, everything is algebraic, so we are in algebraic thing, L is algebraic, so and these are contained, so these are also algebraic. So when you look for mu x comma E dash and mu x comma E, then which degree you can say it will be the big like, so if I write this, which side can you say?
Greater than equal to.
Greater than or equal to, exactly. So why? Because E dash has lesser number of, like, E dash is smaller than E, so the coefficients coefficients are limited for E dash compared to E, right? So in our example, for like this example we have taken, so degree of, if you have a smaller
No,
field,
or we can simply say that E dash of x, like, is contained within E of x. So any polynomial within is contained within E of x. Therefore, any minimal polynomial will be there. So
even more, so I
so
mean
even
to
more.
say,
That's right. So that's why the degree has to be at least equal to.
even I'm claiming this also. So you have this, or maybe other side if I write, so mu of x comma E will divide mu of x comma E dash. Why? Because just consider this, so you have E dash and you have mu x comma E. Okay, so when so in the case of let's say this mu x comma e, you consider this. So this is the collection of, so from this usual thing we do. So this is mu x comma e. It is generated by, kernel is generated by mu x comma e, and that is the least degree polynomial which set in ex, which is satisfied by this x, like x is a zero of that polynomial. That means, and you also know that e dash is contained in e. So this implies mu x comma e dash will belong to e of x also, right? You have, so let me write in a proper way. So what I'm saying, you have mu x comma e, since mu e dash is contained in e, so mu x comma e dash, which is a polynomial in e dash with coefficients in e dash, right? So that will belong to ex, right? So mu x comma e dash will belong to e, this variable x, right? Because coefficients are in e dash, and it is in e dash, that means it is also in e, because e dash is contained in e. So, and you also know that mu x comma e dash, when you evaluate at x, it will be just 0. So this implies mu x comma e dash belongs to kernel of this map, usual map, evaluation map of x. Now I am thinking about e, right? Kernel of epsilon x comma e, which is the map. So which is the map? So you have epsilon x comma e, and you map from ex to you're mapping to L, and then from this what will you get? You will get mu x comma e is isomorphic to e x, right? This is the thing you always have. This is e
We can
algebra.
also do this using division algorithm, right?
Sorry?
We can also say the same thing using division, Euclid's division algorithm.
Exactly. These are, so this is coming. So when you try to get this is also using somewhere division algorithm. So so exactly. So mu x comma e dash will be in the kernel of this map. So, and you know that kernel is this. So that means kernel is generated by mu x comma e. That means all the elements will be some multiple of mu x comma e. So this implies mu x comma e will divide mu x comma e dash. This is a general statement. I have not used anything. If some field is contained in another, and these are all algebraic, so the minimal polynomial of the smaller field, minimal polynomial of the bigger field will minimal polynomial of some element x in bigger field will divide minimal polynomial of the same element in this smaller field. So this is the relation you always have. Okay, is that clear? So now you know that mu x comma e will divide mu x comma e dash, and you know that so that means, and you know that this is equal to b0 plus b1x plus up to and so on b. So you have something b m minus 1 x raised to power m minus 1 plus x. So this is given, mu x comma e is given to be this, and now you know that all the coefficients are there, right? All the coefficients are there, so it cannot be, so this exactly will be here also. So what I mean to say, so since this divides, okay, so firstly I'm just trying to write proper argument. So you have this implies degree of mu x comma e will be bigger than degree of mu x comma e dash. right? There are two things you have. So this is given to be mu x comma e, and now you also know that b0 plus b1x, this same one also belongs to e dash x. And you know that this polynomial, let's say g of x, when you evaluate this g over the element x, this is 0. So this implies this gx will divide mu of x comma e dash, because it belongs to e dash, and it is 0 when you evaluate at x. So this is in the kernel. So gx, sorry, other way around, sorry, because minimal polynomial is always will always have lesser degree than the other polynomial in the kernel. So you have g, okay, so this will divide g. So, and you know that so this is the case, so g has degree exactly equal to mu x comma e. So it does not have any choice, because you have this condition, right, and you have this condition. So this implies mu of x comma, if the degrees are same and these are monic, so that has to be equal. So this is equal to this g. So this implies mu x comma e is equal to mu x comma e dash. So these three things we have now. Is that clear? Is that clear?
Yes, ma'am.
Okay.
Yes.
Okay, great. So as I wrote, so we have three things. First thing, k is contained in e is contained in e dash is contained in ln, which is equal to kx. Second thing, e
dash is contained in e.
oh right, sorry, thank you. So you have this. So ex is equal to e dash x is equal to l, which is equal to kx also. We have this. Third thing, you have mu of x e, sorry, minimal polynomial of x in e and in e dash, both are same. So you have these three conditions. Now let's see what we can conclude from here. So you know that e dash is contained in e. What will I just prove now, so that this will be enough to do? So I need to show that e is equal to e dash, right? Because we have asked so this was the, sorry, yeah, this was the requirement, that e is equal to this k b0 to bm minus 1, which we have assumed to be e dash. So we need to show that e is equal to e dash. So what can I prove? Then we can be done. So it is enough to show. So one containment you already know, and these are vector spaces. So as in the beginning,
Yeah, the containment we need to show, that's it.
yeah, and you can say like equivalent thing also. So one is contained in another, and now you have to show that these are equal. So if you just say these,
E is contained in e dash.
yeah, that we need. So e dash is contained in e.
So if I take any element in e, I'll have to show that it's present in e dash.
Yeah, exactly. But I'm saying some equivalent condition you can prove also. So you can prove that if size are equal. Yeah. So if sizes of e dash and e are equal, then you are also done. And what does it mean to have size in vector space? It's like dimension. It's exactly the dimension. So it is enough to show that dimension of e is same as dimension of over k over the same field. Yeah. Why now I'm saying that dimensions are same? Because these are not infinite. Dimension is not infinite. Why I'm sure about that? Because we already know L is a finite extension. That's why I started with this. So we have proved in the beginning that if L over K is simple plus algebraic, then it is a finite extension. Finite extension means dimension is finite. And whenever dimension is finite, then we can talk about the size in terms of dimension, right? Because if it is infinite, we are still not guaranteed with the, we cannot just prove with the dimension thing. If it is infinite, we cannot conclude anything, right? Since L over K is a finite extension. So this is a finite extension, so every subfield will be a finite extension also. And E and E dash are subfields, so this will be will have finite dimension. Is that okay? Is that okay?
Yes, yes, yes.
Okay, great. So, okay, so when you see dimension E over K and E dash over K, so what we can do, we have minimal polynomial thing also. So we can use this epsilon thing, sorry, evaluation thing. So what I mean to say. So now your fields are E dash and E. Okay, so Ex over minimal polynomial of x over E, this will be isomorphic to E this, right? From this epsilon, now we have x and E. So we are talking over E, we are not talking over K. So everything should be corresponding to whichever field you are taking. Similarly, for E dash also you can write this thing. Okay. And what is Ex? Ex means this is the Ex is L. You already know that E dash x and Ex are L. So this is isomorphic as K algebras. Sorry, E algebras now. E algebra isomorphism, E dash. But from this part and this part, what can we conclude? So you have this, so we can conclude that because we need to go to the dimension. So degree of mu x comma E is same as dimension of L over E, right? And from this, degree of mu x comma E dash is same as dimension of E dash over dimension of L over E dash. Okay. So what does this mean? Now you know that since mu x E is same as mu x in E dash, this implies degree of mu x comma E is same as degree of mu x comma E dash, which will further imply dimension of L over E is same as dimension of L over E dash. So we have these two things now. And now you can use this E dash, this containments. So I am just interested in this part. So as you know that dimensions are finite, I can use the dimension formula. This is same as L over E over E dash, right? And now, so this is another notation for dimension of L over E dash. This is another notation, nothing else, right? So L over E dash is same as L over E, so this will get cancelled. So you will just get this to be equal to 1. E over E dash is 1. So what does this mean? So yeah. So dimension of E will be same as dimension of E dash, or even more. We have E is equal to E dash. Is that okay? So E and E dash, yeah.
I had to reconnect my network due to data
Okay.
limitation. So I have
So
not,
which part?
I have not seen.
Which
I
part
have
you?
not seen. I have getting the point. Dimension. We have to see dimension of L over E is equal to dimension of L over E dash. We have to see up to that point. I have gotten.
Okay.
But
This one, right?
after that discussion, I have not heard.
Okay. So we just use two things. So we got these three conditions. From there we need to conclude that E is equal to E dash. So I said if we just prove E, and even I don't need to write that also, but if you prove dimension of E same as dimension of E dash over the same field which we have taken to be K, then even this, but we have proved other thing means we have proved that E over E dash is equal to 1, which also mean E is equal to E dash, because E dash is contained in E, so the dimension is just 1, so these have to be equal, right? So since these are finite extension, we can talk about the dimension formulas. Okay, so what we did, we used this evaluation maps, both these maps, and from there we have concluded that dimension, since degree of minimal polynomials are same, dimension of L over E and E dash will be same from these two things. And from there we have used this L over E over E dash, so this thing, the formula, and then we know that L over E dash and L over E are same, dimensions are same, so we can cancel it out, so we just get E over E dash to be equal to 1, and which will imply E is equal to E dash.
E over E dash equal to 1.
So this means you have this containment and the extension is just 1. So what does this mean? You can just generate E dash by attaching 1. So maybe if you want to write basis of E over E dash is just this 1. This means just one element is there, which will imply that these are same, right?
Yes.
Yeah. So this is the proof. Okay, I hope you all have understood this. Okay, yeah, great. So let's see this part. Even I'm cropping this hint. Anyway, I am going to explain that, so no need to worry. So yeah, this is better. So I'll use hint only, don't worry. So okay, small but strong question. So L over K is given to be a algebraic extension. So this is a algebraic field extension L over K. So it is saying that to show L over K is simple, that is there is a primitive element x such that you can write L to be Kx, simple if and only if there are only finitely many intermediate subfields. So what does this mean? So you have L, you have K, so there are many fields in between, maybe some chain, I don't know, so many subfields. So okay, let's say E1, E2, E3, we don't know if we can enumerate also, it could be uncountable. Okay, so there are fields in between. So the condition says L over K is simple, then there are only finitely many intermediate subfields. This is a if and only if condition. If L over K is given to be algebraic, that is also a condition which we have to use. I hope question is clear. So intermediate subfields, these are intermediate subfields in between.
Yes, question clear.
So we have to prove that these are finite. Okay, if L over K is simple. So let's try to prove. So I'm proving this direct part. So L over K is simple plus algebraic again. Right? So this is given. L over K is simple plus algebraic. Algebraic is given in the question itself. Okay. Okay. One more thing. Let's assume this set to be calligraphic J L over K, or maybe I'm just using same notation as hint. So this is equal to all E is a field, E field satisfying containment. So L is a intermediate field. So this is exactly the set of intermediate subfields. Okay, so we have to prove that this set is finite. Okay, so in the direct part we have to show that, so L over K is given to be simple plus algebraic. Okay, so we have to prove this calligraphic J, L, comma K is finite. Okay, there are finitely many fields in between K and L. Okay, so how shall we start? Okay, in the first question, what have you done exactly? Let's observe that we have taken L, so there is K. So it is saying if E is there, if in between E is there, I can use first question in this part at least, because it is simple. L is simple and algebraic over K. In the part A, we have these hypotheses only, like this is L over K is simple and algebraic. Okay, so and it is saying if there is some E, okay, then this is equal to K with some coefficients, where coefficients are coming from this minimal polynomial of, so L is some kx, because this is simple, so there is some primitive element x. So this these bi's are coming from mu x comma k, which is equal to b0 plus up to and so on, bm minus 1 x raised to power m minus 1 plus x raised to power m, right?
So over here we can argue that, so let's say that in K, the minimum polynomial of x will be power degree n.
Right.
Then in every subfield of L, the minimum polynomial degree has to be less than or equal to n.
Right.
So there are only finitely many possibilities now, right?
One more thing, you are using one more condition, not just degree argument. You have to say that this divide also, because if so there are many polynomials, but it should satisfy x, right? So
Right.
yeah, so we have this division also. Otherwise, for a fixed degree n, we can have plenty of n degree polynomials with different coefficient, which might not have 0 x, right? So we are using two conditions. Yeah, exactly as you said. So let's do in a formal way. So let's define a set D, dx, that is all the polynomials g, where g is a divisor of mu x comma k. So I have not written that exactly there, but yeah, so this condition which I proved here, if e dash is contained in E, then, and if x is algebraic, then mu x comma E, the minimal polynomial of x in the bigger field will divide a minimal polynomial of x in the smaller field. So this condition we are saying. So as you have, so for in your in what we have, E is contained in L, so that means minimal not like this. So you understood. So E and E dash could be any subfields. Okay. So this is a general thing. We have not used anything else here. Okay. So what does this say? So this says, so in our situation we need this. Since K is contained in E, this implies mu x in the bigger field so bigger field is E, this will divide mu x comma k. Okay, so basically if there is a subfield, so there is this gen, but we are interested in this. So there is a subfield of L which contain k, then mu x comma e will divide mu x comma k. So we are saying wherever there is a subfield, then we can talk about this minimal polynomial business, like if we are interested in that, because in this part we are interested in the minimal polynomial. So we took dx to be the set. Let's just say dx is the set of all the polynomials, monic polynomials. So g monic and divisor of mu x comma k. Okay, so monic is important because we want to talk about minimal polynomial. Okay. Also, if mu x comma k is monic, that does not imply that all the divisors will be monic, because here we have inverses, so we can have any unit into that G.
Would it not be implied that it would be monic? Because
No, no,
otherwise,
no.
because it's a field, I can
Hmm.
just divide by
No.
whatever the coefficient of the highest degree is and get a monic polynomial.
Yeah. So mu x comma k is monic. But when you say there is a divisor, so divisor means what? Divisor means in the formal definition, mu x comma k is something g x into some hx, right? Now here you can also have hx to be some unit. Let's say in q let's say you have 2, so 2gx uh, oh, okay, sorry, what I mean to say, let me say that. So what you can have, let's say uh, uh, so gx could be, so let me give an example itself. So you have x square minus 2, and you have something, let's say this. Okay, and you have x minus x plus root 2. So still what you can write, you can assume this to be something like 2 into x minus root 2, and here you can assume it to be this. So this is your hx and this is your gx. So divisors are with units always, because 2 is invertible here. So this is this polynomial gx is a divisor of x square minus 2. It is not so in z, in n, m by n, so what I mean to say, so when you are in z, then minus 1 and 1 could be the 1 are the units, so there you will not get 2 and 3, right? But here when the 2 like in q, 2 is invertible, so you can have this 2 as a multiple, because from the divisor definition it just say this, there is some h such that gx mu xk can be written as gx into hx, and there you can have units. So that's why we have to say monic. If we want to just consider, like we can still consider equivalence classes here, like we can so basically what we want to say, there is x minus root 2 also, there is 2x minus root 2 also, but we don't want to consider these two as separate entities, because we are interested in monic polynomials, because we will talk about minimal polynomial only. So we don't want these to be different in our set. That's why we have to write monic. Is that okay?
Yeah, fine.
Okay. Yeah. So yeah. So divide does not mean like it should divide. So there could be units always in multiplication. Okay. So yeah, let's see what do we have now. So so monic and divisor. So now let's define a map. Let's say phi dx to this j l comma k. So this is the set of all the fields, all the intermediate fields. So
Ma'am, please
yeah,
keep the page.
sorry, come again. Come again, like what were you asking? Okay, anyway, so yeah, dx is this. So define a map which say so there is a polynomial here, so you map b0 plus b1x plus up to and so on b let's say n minus 1 9, it doesn't matter any variables. So you have x raised to power n, because you have monic polynomials here, so you consider any monic polynomial and map it to k b0 b1 up to and so on bn minus 1. Okay, okay, define a map like this. Okay, so we claim that phi is surjective. Okay, firstly, this map is well defined. How will you say that? If you take two polynomials, so you have monic polynomials, right? So if two monic polynomials are equal, then that means you have some different variable here, right? So what I mean to say, if you have any monic polynomial, it will map to just this element. There will be well definedness means if you have any element that should not map to two elements, right? For the definition of function, it's this is the well definedness. So you take any monic polynomial, you map it to kb0 to bn minus 1, that is unique. And and every element has a image, so this is well defined. Okay, so we are saying that this map is surjective. So what does this mean? Surjective means you consider any subfield, then you should get a pre-image, right? So let E be a subfield of, so or maybe if you want, so let E belongs to this set J L comma K. That means this implies this is the containment we have. Okay, now we need to find a polynomial such which divides mu x comma k, right? Or maybe, okay, so we have this, we need to write in this term, right? That's why we only then we can say that this is a surjective map. We need a pre-image. So yeah, KEL. So where should I start? So I need to write E in like this. So what can you say? Yeah.
And from the previous theorem.
Exactly, from part 1.
Because
yeah, exactly, very good. So from part A, we know that E will be equal to K some, okay, I'm using different notation just to not misunderstood with this phi definition of phi. So you have some this where mu x comma E, sorry, yeah, mu x comma E is equal to a0 plus a1x up to and so on am minus 1 x raised to power m minus 1 plus x raised to power m. Exactly, right? So you have E is equal to this. So from part A we have written this down. Now what we have to prove that this so we have this setting that E is equal to k0 to am minus 1, where this is this mu x comma E is this. Now to say that this is exactly the pre-image, what we have to say, that mu x comma E should be a divisor of mu x comma k, right? Is that okay? So to show, which we already did, but what two things we required? So there is a you consider a subfield, then from part A we can write E to be equal to exactly this, where these AIs are coming from the minimal polynomial of x over E. Now if we want to say that mu x comma e is exactly the pre-image in dx, we have to say, and what is the set dx? Dx is the set of all the monic divisors of mu x comma k. So we have to say that this is a divisor of mu x comma k, which we also did here, as I wrote earlier. So this part, if something is contained in e dash is contained in e, then so we have proved this part, right? So mu x comma e will divide monic polynomial of x in the bigger field, will divide minimal polynomial of x in the smaller field. Is that okay? If you have any doubt, just let me know, I can explain again. Yeah. So we have proved that this mu x comma e, phi of this is exactly your e. We have proved this. So surjectivity is done. This implies, since e is an arbitrary element of j, l comma k, this implies phi is surjective. And since phi is surjective, what does this mean? Phi is a map from dx to j, l comma k. So this is the set of all the subfields. This is the set of monic divisors of mu x comma k, minimal polynomial of x in over k. Right? So this is surjective. What does this mean about? So we need the cardinality of this set. Since the map is surjective, yeah.
Here to show that mu x x comma e divide mu x comma k. This line should
Okay, let me explain this. So okay, let's do this. So we have to prove that mu x, so this is a general statement. Let's say anything. So k is contained in e. Okay, so claim is mu x comma k
e
will divide sorry, other way around.
e however x
Yeah, e
e divide
exactly.
okay.
So how will we do it? Let's start with this. So we have so yeah, so mu x comma k sorry, yeah, so let's do this. So you have mu x comma k, this belongs to kernel of okay, so you have this map ex over mu x comma e okay. So what does this mean? So okay, so mu x comma k of so this belongs to your kernel of okay, so I want to write in a better way, but okay, so you have mu x comma e, you know that this is equal to 0. So what does this mean? Mu x comma e belongs to kernel of so this is the kernel, so it's exactly, this is the epsilon map, epsilon of x in e. So epsilon means evaluation, we mean e of x e. So you have this, right? Now what we are saying, so this is from this part. Now let's see what this is. Mu x comma k, when you evaluate this over x, what will you get? You will get 0,
Yes.
because this is a minimal polynomial of x over k, and when you evaluate at x you will get 0, right? Now now since k is contained in e, right? So this implies this polynomial, when you take this polynomial like with variable x, this polynomial itself will belong to ex. So you know that this belongs to kx, right? Because this is a minimal polynomial of x with coefficients in k, and this is contained in Ex, because K is contained in E, that means Kx is contained in Ex. So this implies mu xk belongs to Ex. And now you also know that mu xk, when you evaluate at x, is 0. So these two things will imply that mu xk, which is polynomial, this belongs to kernel of this map epsilon x comma k, x comma e, because we are interested in E thing. So you know that this polynomial belongs to Ex, and when you evaluate at x, that will give 0. So this polynomial will be in the kernel of this map, right? This map. So what does this mean? This implies, and now you know that what is kernel. Kernel is generated by mu x comma e.
Yes.
So what does this mean? This will mean this polynomial should divide this.
Okay.
This is a multiple, and that's exactly we did.
Okay. That is surjectivity is done.
Yeah, that's why. So for surjectivity, we needed two things. We used first part, which says that there is some polynomial, which whose coefficients, when you attach with the k, you will get the subfield. And now you need to show that this polynomial itself belong to dx. That means it is a divisor of mu xk. And then you use this part. So that means this belongs to dx, and we are done. So this map is surjective. And now when it is surjective, you have, what do you have? Surjective means you, in the right hand side, you have lesser things than the domain, right? Codomain is exactly your image. So image, the cardinality of image is always less than or equal to cardinality of the domain, right? If it is injected, then it will be equal. But again, we exactly. We can talk about this because the cardinality of dx is finite. So again, when we write is less than or equal to, then we cannot talk about the infinite things, right? So we already know that dx is finite. Why? Because dx is the set of divisors. Is the set of divisors of a fixed degree n, like of a fixed polynomial. So how many divisors it can have? At most, one more thing. So for example, mu xk is some polynomial. We were writing, I don't know, some other coefficient. Let's write c1x cn, cn minus 1x raised to power n minus 1 plus cn. Some n is any natural number, and so you have this. So mu xk is equal to this. So how many divisors it can have? So one more thing, you always remember that firstly you can reduce it by the prime factorization. You can reduce it to some irreducibles, right? So now when you extend your field, so in k this is irreducible. So in k, mu xk is irreducible. But when you go beyond k, like you take bigger field than k, then there might be some factors which can split it out from this polynomial, as we did for this example. So the example of this. So in this example, you know that when you extend the field, minimal polynomial degree can go down, or it will be just some factor of the previous one. But how many factors it could have? So what maximum can have? So this I am answering one more question. Okay. Should I include with this part this question? Because it will help me to discuss this question also. So what I'm saying, don't get confused. So this is a finite simple extension. So this is a finite extension. So this is algebraic. So we are exactly in the this direct part of question 2.1, right? not 2.1, this is 1.1. So I'm considering this question. This question says if L is equal to kx, which is a finite simple extension of a field K of degree n, and now you have given the degree also. So degree n, what is the degree? Degree is exactly the degree of minimal polynomial, right? Because what is kx from this evaluation thing? You know that this is equal to, and this is your L. So degree is given to be n. What does this imply? Mu degree of mu xk is equal to dimension of kx over k, which is given to be n. So degree of minimal polynomial is given to be n. Okay, so we are in the situation that you have minimal polynomial degree to be n. Same situation. Now we have to count how many intermediate fields it could have. So we have just proved that it is dx. We have just proved this j l comma k. This is surjective. So how many intermediate fields it can have? So j l comma k should be less than or equal to this. So if we are able to talk about the cardinality of this set, then we are done, right? Because this is bounded by cardinality of dx. So let's see how many it can be. Okay, so that's exactly will answer, because we know that this is finite. If you know that this is finite, then we are done with the first part. But let's calculate this cardinality also, because this will answer this 5.2 also. So is that okay? Where are we exactly? Are you with me?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, great. So let's calculate what is the cardinality of dx. So what is dx? Set of monic divisors of mu x comma k, and which has degree not equal, degree is degree n. Okay, so what mu x, so we need monic divisor. So what it could have, as I said, when you go beyond, so we are in the situation that you have k, you have e, you have l. So when you go in the bigger field, what could happen, that you get the irreducible could be reduced in e. Like if there is a reducible in k, then it could be reducible in e, as we did for q cube root of 3. So basically it could split more. That is the main agenda. But how much? Okay, so we can write. So let's use Kroneker's theorem. What does this say? This theorem says that there exists a field, let's say f. There exists a field f, extension of, so which there exists a field f containing k, because we are talking about the minimal polynomial of k, containing k, such that mu xk splits completely in linear factors, which is splits completely in linear factors in fx. So there is this field where you can get as we did in q. So when you attach all the roots like omega and cube root of 3, then in this field it will split completely. Okay, that x cube minus 2 will split completely in this thing. So that is the maximum we can have, right? Maximum thing. And so what are all the factors? You will have something, let's say mu x comma f, let's say this, this will be first element, you always have x minus x, right? And you will have something like let's say x minus a1 up to and so on. Let's say a2 1 is already there, so this is x minus an. These could be same also, these ais could be like a2 is same, a2 could be same as a3, that could happen, like square could be there. But so in some splitting field it can split, so that is the maximum could happen. Now what you need to find, you need to find other monic minimal polynomials of some other fields. So basically you need the divisors of mu xf, mu xk. Also one more thing you need, divisors of mu xk. That's okay. Okay, so one more thing we need when what we did, we are interested in this part mu x comma e. So we already know it should be a divisor which has this factor, because it should be a minimal polynomial of x first. So what we are saying, so you have this situation k, and now you have this situation says that e means you have some e just me if L is equal to kx, then e is similar to giving mu x e. And what is mu x e? It should be something with a factor x minus x in the splitting field. We are not saying it will split here, but there will be a factor x minus x, so that is always there. Now the other factors could come, or maybe cannot come, right? So how many minimal polynomials like this you can get in different fields? So you have this, and now you are saying this factor will always occur because we need minimal polynomial of x. Now other factors might be there, might not be there. So what are all the options you can have? So we are interested in all mu x comma e, where e is in between k and x, L, and mu x. So you know that already, we don't need to write this as a condition, but this is always there, this is always true. So we are interested in the cardinality of this set. So this cardinality is not same as D, first thing which I should say, because D need not have x minus x as a factor. So we are also putting a restriction, one more restriction, which says that this is a minimal polynomial of x. So even we can modify this question, like we can modify D as per this choice, but that is also okay because divisors are finite. Of finite degree, we have finitely many divisors, right? So for any fx, and this has some degree, let's say n degree, then divisors will be finite, right? Finite. Is that okay? Am I confusing?
Yes. Finite degree, so obviously devices should be finite number.
Exactly. Yeah. So this is not exactly D. Why? Because x minus alpha. So we are interested in this set. So because question is asking how many subfields you can have, how many number of intermediate fields you can have, right? So that we have to show that this is equal. It is at most 2 raised to power n minus 1.
Is equal to 2 to the power n minus 1.
Yeah, we need to prove that. Now we have explained now that to find the intermediate field, it's same as finding a minimal polynomial of x in that field, right? So finding a e is same as finding mu x comma e. And what is mu x comma e? It is a divisor of mu x comma k with a part like x minus alpha is always there because it should be a minimal polynomial of x, right? So this, okay, so this is the case. So this set is same as finding mu x comma e, where or maybe divisors of mu x comma k with x minus x minus x, always a factor. So this will always be a factor because it should be a minimal polynomial of x. That condition we need. So this means, so can you tell me how many will it be? So mu x comma f we already wrote like this. So you have this and there is some n minus 1 factors. So let's say a1, a2, x minus an, right? So what could happen? We don't know. We are not calculating exactly. We don't know AIs are what. It could be same, it could be different. We don't care. But if how many divisors you can have from this containing this factor. So whether this can come or this cannot come. So how many will it be? The cardinality?
At least n minus 1.
Exactly. Very good. So the cardinality will be exactly 2 raised to power n minus 1. Because x minus alpha will always be there. So this factor can come or this cannot come. So there are two options for this factor, that is either it can come, either it cannot come. Similarly you have options, so number of ways you have to find, yeah, number of divisors you have to find, 2 into 2 into up to and so on 2. And how many are there?
So
N minus
splitting
1.
on the right hand side is in the field L, right?
Sorry?
The splitting on the right hand side is based on the field L.
Yeah.
Okay.
But we don't know about L. We are talking about the maximum thing. So we are talking about so if you want to say like this, that is also fine. So I am talking about the maximum thing. L could be same as F. L cannot be same as F.
No. I'm saying
yeah,
this splitting that is done is with respect to L.
Okay. So.
So because otherwise it will not be the minimal polynomial now.
Right. I agree with this. I am saying how many it can be. So just for explanation. But okay, as you said. So because I want to explain about x minus x, that's why I should explain like this. Otherwise, what you can have, you will have. So you will have something like this. P1, let's say pmx, because x minus alpha need not appear exactly like x minus alpha. It will be in some irreducible because we are talking about minimal polynomial, right? So so not L, this is equal to mu x comma L. So in mu x comma L, it will be in some okay, that is one more thing I should not write. Okay. Okay, let's do this. So you have mu x comma k and you have okay, yeah, let me write like this. So you have this L over k. Okay, so mu x comma k is there in kx. Now if you think mu x comma k in Lx, it will be in Lx, it will be mu x comma k x, sorry, will be equal to some bunch of irreducibles in Lx. Like we have increased the field size, so it can split, right? It can split in some irreducible. We are not sure if this is a splitting field, so it will split in linear factors, but it might split, it might not split, we don't know. But let's say these PIs are where PIs are irreducibles. Is that okay, this statement? So think about mu xk, which is a minimal polynomial of x in k. Now you just see this polynomial in the bigger field Lx, as we did earlier. So for example, if L is equal to your q, cube root of 2 omega. Yeah, then so with this you know that and you have k to be just q, then you have x cube minus 2 here. Now same polynomial will look like x minus okay, let me write just this, because otherwise again it will not split. So the same polynomial will look like this, and x square plus cube root of 2x plus cube root of 2 square. It's same polynomial. Now it has split it in two factors, just this. So there are some irreducibles which are in Lx. Okay, now here you know that x minus, so you are interested in divisors of this, uh, with the condition that x minus x should be a factor. X minus x should divide this divisor, like divisor gx. Okay, divisor just g, let's write gx in some splitting field. Okay, so when I'm writing divide, that means it should divide in some sense of splitting. Okay, because if it is irreducible, we cannot say in some splitting field, in this splitting field, not some, in this splitting field of x. Okay, whatever. Yeah, is that okay? So we are interested in this set. So x minus, so whatever, we can say p1x could be your choice for minimal polynomial, which explains that its coefficients are coming from. So what you can do, you take p1x. Now the coefficients, so yeah, exactly, yeah, okay, we can explain like this. So you have p1x, pmx, and this is exactly mu x comma k in Lx. Okay, so now now wherever x minus alpha is appearing, okay, wherever it is appearing, we are interested in that firstly. Now let's say x minus alpha appear here, so we can take this to be your to be the minimal polynomial corresponding to the coefficients of coming up in this polynomial, right? You just take k with these coefficients of p1x. Okay, so this is the case. Now just a second. Okay, yeah, so these are coefficients of p1x, and then we are done. uh, so I that's there is this x minus x, that's why I use this splitting polynomial, but that's okay. Now what are all the choices you can have? Either you can have p1x, either you cannot have p1x. So you take irreducibles, and okay, so either you can have this factor, either you can have this factor, or maybe you can write like this. So you write x minus alpha, and there are this other factors in the splitting field. I have to say in the splitting field. So you have the choices that this could be there, this might not be there. So you can have how many options you can have? Let's say this is m minus 1, so I started with 2, so this is this. And now what maximum m could be, because these could be linear factors also, right? So this is less than 2 raised to power n minus 1. So maybe L is the splitting field, L might not be the splitting field, but whatever it is, we don't care, right? So it is upper bound by 2 raised to power n minus 1, because x minus x we always want with us, because we want the minimal polynomial of x.
Ultimately, it has to be reduced in simple, say 1 degree
Hmm.
polynomial. That
Hmm.
is why at most n to the power n minus 1.
Yeah, yeah. So there is always one factor we want. That's what we are saying.
Ma'am, always one factor x minus capital X minus small x. So
That
this factor always comes in every whatever field I have taken.
Yeah, exactly, whatever field we will take, we want mu. So we are interested in, okay, so we are interested in E. That means we are interested in mu x comma E. And what is mu x comma E? Mu x comma E is coming from this condition, and this condition also says mu, you have this divides, this is a divisor of mu x comma k.
Yeah.
Okay, so this is a divisor of mu x comma k, and this should be a minimal polynomial of x. So you always want x should be there, right? X should be like x should be a factor of this minimal polynomial wherever it factors, but x should be a factor of this minimal polynomial. So x minus x you always want with you in the polynomial you are choosing.
Intermediate any field you have
Yeah,
taken.
so that's why x minus x will always be there, and the other factors could vary. It might be there, it might
Uh,
not be there. If it is very small field, L is very small that it does not even factor, we just have maybe one option. We don't care. The maximum we can have to be this. Okay, so the
okay.
cardinality of this set is 2 raised to power n minus 1. That's exactly we needed. So now you can try to find the examples also where the inequality is very strict, like that means it is strictly less than 2 raised to power um, what.
So, ma'am, we have to, when it is suffices to show that at least one factor of them is not split into linear factor.
Yeah, so at least one factor does not split in L. So for example, you consider this example. Let's take this example itself. uh, yeah, this one. So in this situation you have seen you have 3 and you have this. Okay, now so how many intermediate fields you can have? So so you have cube root of 2. Actually, you cannot have much factor. Okay. So in this situation, it says 2 raised to power L O. So n is the minimal polynomial. Minimal polynomial is of degree 3. So 3 minus 1, that is 2 raised to power 2, that is 4. Right?
Hmm.
So that is the case with k. So this is the degree of mu x comma q. Okay. So what were we saying? Yeah, sorry. So we are saying you can have at most 4 factors. Okay, at most yeah, 4 factors. So if you take L to be cube root of 2, then how many in between you can have? So in this situation you get a splitting field, not the splitting field, you get this, right? We are not saying this is the splitting field of x cube minus 2, right? So how many in between you can have with this factor? Like this factor should be there. So there are no, actually there no means there are just two, q and q cube root of 2.
Hmm.
There are no other. So the k and l are also included, so you have to find these subsets. So E can be k or l. There is no anything in between, because you have to find the divisors of this. So divisors of this will contain this part.
This
Okay.
but or no other linear factor that they are present.
Yeah, and this will not factor. This part will never factor, and
Factor.
this does not have cube root of 2 as a root, so we cannot take this part also. So you have no other choice, so there are just two choices. Okay, so there are two choices, but from the cardinality we need 4. At most it can have 4, so this is the strict containment. And similarly, if you take L to be cube root of 2 comma omega, like I'm taking bigger field, if L is equal to this, okay, then it will have all the 4 factors, because this can also factor. So there are 2 factors of this. Now you can take x minus cube root of 2 with this factors, one factor, and then you can take second factor, so you have all the 4 possibilities. So this is the case. Okay, great. So let's complete the earlier part, which I should do at least. So yeah, right. So in K, mu xk is irreducible, exactly. So this is finite, we are done. So let's prove the other side. Okay, so other side says, so to show, now assume this set, the set of fields in between K and L. This is if this is finite, then L is L is simple. We need to prove this. L is algebraic is given in the question itself, so there is no issue. Okay.
It is other side. One side we have proved.
Yeah, we proved.
Then even only condition. It was.
Sorry.
It was even only condition.
Yeah.
One implication we have already done.
Exactly. So we need to prove this part now.
That's what is.
Yeah. So let's take first condition. If if K is fine, so case 1 maybe. Case 1. K is finite. What does this mean? If K is finite and it is given that, so L is there, K is there are finitely many intermediates. Okay, so finitely many. So what you can do, and how the this finite fields will look like. Okay, there is something which I will use. So I am saying that this K, so L over K we are talking about. So this is something, yeah, so it will be something like, let's say x1, this will be, let's say, K x1 x2. So this, okay, so this is a tree we use. So you have L, you have K. There might be, you can have x1 x2 x3, and there is like x1 x2. So it will be like this. There will always be a tree like this. Now you can have kx1 and say, let's say here, but there are finitely many. So I am claiming that L will be equal to kx1 up to and so on, some let's say other variables, not variables, some other elements. I'm not talking about these x's. There could be others also, k, y1. There could be many. But whatever it will be finitely many. So the number of elements now, so L you can write it to be k y1 to yn, like something like this. Okay? Is that okay?
Yeah. Case one, you have break into case one. K is finite. We have it is as per given condition, the divisor set cardinality is finite. It is.
We cannot use that argument, because we already know it is not simple right now. We have to prove that this set is L is simple. So we don't know L is equal to kx or not. So we cannot use this first part, second part, whatever we have done till now.
Okay.
Yeah.
Okay.
So divisor's argument right now, we have to prove this, so divisor's argument won't work. Even finiteness we are not using right now. I'm saying, like, if you have L, you have K, and there are some in between finitely
Hmm.
many intermediate fields, then it will be of kind kx1. So for example, let's say if this is a infinite thing, let's say this is infinite, then you will also have this chain, because if these are not equal, then this will go up to this infinite thing.
Okay. Hmm.
Okay, so it will has to stop somewhere. So that means the elements will be, so this is for everything, so that means this has to be finite.
Okay.
These numbers we are using, sorry, elements has to be finite.
Hmm.
Now you know that L is over K and K is finite, and finite fields means, finite fields are what, are of the are of the form some power, like
Ah,
k p
yes,
raised to
yes.
power n, number
Ah,
of elements will be some power of prime. Now k is some extension of it, so k will have characteristic p, of course. Now k is equal to k y1 up to and so on yn. So, and you know that degree will be what, since these are finitely many and yi's are algebraic, so you know that this is algebraic, because it is given that L is an algebraic extension. So k, so I'm using this k y1 up to and so on yn over k, because it is algebraic it has to be finite, my claim is this. So you take, by induction I can say this, yn k y1 yn minus 1. So I'll split in all the parts. Okay, so on. So you'll get at the end maybe. Okay, so this is some multiplication. So this will also be finite extension. So you have finite field and you have finite extension. So all algebraic extension need not be finite. Firstly, I have already said. So this is a finite extension. Finite extension of a finite field, what will it imply? What, how many elements will have? Number of elements, not even, so number of elements will be how many, this will be finite because the set is finite. And now vector space dimension is all okay. So L over K, if this is n, if this is m, then how many elements will it have? Cardinality of k raised to power m, right?
hmm. Yes,
So
yes.
in our case it is exactly this, and cardinality of k is given to be p raised to power m. So this will also be finite.
Hmm.
Now since this is a finite field, this implies L is a finite field. So again this will be some power of this, and actually we have written already. So this is a power of nm power of p, right? So this
Hmm.
implies, so L cross will be cyclic, because finite field, finite subgroup, you know that. So this is cyclic. This implies there exists some x belongs to L cross.
L cross मतलब L cross
L cross means multiplicative group,
oh
that
अच्छा okay
is
okay हाँ हाँ हाँ
L
cyclic
minus
okay
0.
हाँ
Yeah,
okay
that
okay
is cyclic. We have proved that
yes yes
in the lectures. So there exists x belongs to L cross, because this is cyclic. L cross can be generated by one element, right?
yes yes
Now what you can do, you can write L to be exactly equal to kx, because you need just 0. So when you take k0 you have 0, kx you have 0. From x you have L star, full L star. So you can write L to be equal to exactly kx. Is that okay? So L cross is equal to generated by x. That means it is all the powers, right? Even 1 also. So you will have 1x x square. It will stop somewhere because this is finite. So let me write like this. So x square, x raised to power, let's say p raised to power nm, we are talking about minus 1, even minus 2 now, and this will be 1, because cardinality of L star is what? P raised to power nm
Yeah.
minus 1. So this L cross will be exactly this. So these are all the powers of x. Now what is L? L is equal to 0 union this set, right?
Hmm. Yes, it.
So yeah, so you can write this to be equal to, because kx has all the powers of x. So I'm just writing, I'm not giving too much actually. K will be there also, but I'm saying you can write it to be equal to kx, because kx will have all the powers of x, so all the this part will be there. And from k, so k says kx is the smallest field which contain x and k, right? So this will be equal to 0 will also be there. One more thing, so at least you can say this. Now from other containment, what can you say? Since x belongs to L and k is also a subset of L, this implies kx will also be there. So both side containment is there, because this is the smallest subfield which contain x and k.
Yeah, okay. Yeah.
That's why L is equal to kx. So there is this argument we can use always if we need. So this implies L is simple as we required. So this is the case
I
of.
couldn't find required in
Sorry.
your Apple Music library.
Okay.
You can ask me to play a radio station or ask for.
Yes. Okay. Siri. Okay, so case 2 is k is infinite. Let's talk about this. Okay, if k is infinite, now you have to prove again that this is L is simple. We know that L is algebraic. We already know this is algebraic. We know that the set J, L over K, is finite. We know this much. Now we have to prove that as L is simple. So first you can start like this. So you know that Kx, x belongs to L. So this is a set of some fields, subfields, some subfields of L containing K, right? So this is a set of some subfields of L containing K. Now you know that this will be contained in, this set will be contained in this set J, right? So this implies this Kx, x belongs to L, will be finite, because this is finite. So what we are saying, you take all the sets of type K attached with one element. So like simple fields. Okay, you take simple fields Kx, where x is varying. So x could be any element of L. Since you know that these are all the subfields of L containing K, it should be in this set. And so this means this should be finite. Now since this is finite, this set is finite, what does this mean? Yeah, so this set is finite. So now what you can take, consider x, or maybe let's say alpha, consider k alpha, which is maximal, or maybe better way, consider, or maybe pick k alpha maximal in terms of dimension. So what we are saying, you have something L, you have K, you have like Kx, you could have some other element ky, something like that. So in particular chain, you can have chain like this. Okay, you can have, let's say, k, you have some better element, let's say x plus z, something like that, I don't know. So you consider a chain and you pick the maximal one. Okay, so like in this situation you pick the maximal one. There could be many, there could be some other from this direction, so ky is maximal if there is no other in between, but you pick one maximal. Okay, maximal means this implies that is, consider sorry, that is, there does not exist any k beta, there does not exist beta in L such that k alpha is contained in k beta, and which is not equal, and this is not equal to not even okay, yeah, so it might be equal to L, we don't care. So yeah, this set is something like you are picking the maximal one, we don't care if this is equal to L or not. Okay, so this is contained in L, this might be equal, this might not be equal. Okay, but it should be, if L is of the kind k beta, then we should consider the maximal one, that is L itself. Okay, so there should not exist in between k alpha and L, there should not exist anything such that which is of the kind just one element, like simple field you should not have. Okay, so let's see, we have picked this. Okay, where alpha belongs to L. Now okay, claim we claim that L is equal to exactly this k alpha. Okay, we claim that L is equal to k alpha. Suppose not, so assume the contrary, suppose not, that is, there exists some, let's say, beta belongs to L such that or maybe there exists beta belongs to L which is not in k alpha. If these are not equal, you already know k alpha is in L, because alpha is in L and k is in L, so k alpha is contained in L. Okay, so there exists some, let's say there exists some beta which is in L but not in k alpha. Now consider this set. So you write k alpha plus c, some constant c, and you write this, and c is varying in this k. So you consider this set k alpha plus c beta. So alpha plus c beta is again an element. Okay, now this set again will be finite because these are subfields, because alpha is in L, beta is in L, so this set will be in L. So these are subfields of L which contain k, of course, because k is there. So you have this set. Now although c belongs to k, since this is finite and k is infinite, we have assumed this case 2 says k is infinite. Since k is infinite, this implies there exists some c1 and c2 belongs to k distinct such that alpha plus c1 beta k is same as, so this field is same as the other field. Okay, so with c1 and c2, these both sets are same. Okay, these both subfields are same. Now if this is the case, then what should we write? So yeah, so what we were doing, yeah, this is c1 and c2 are distinct, that is important. Okay, so consider then alpha plus c1 beta and alpha plus c2 beta belongs to this, because these are same, So you just consider any of these. So both of these elements should belong in this set, in the subfield. So this implies C1 minus C2. You consider this element because Ci's are in K, so inverses will be there. So C1 minus C2 inverse you consider, and you consider this minus alpha plus C2 beta. This belongs to K alpha plus C1 beta, and this implies C1 minus C2 inverse. So alpha will get cancelled, you will get C1 minus C2 beta, and these are also inverses. So you will actually get, this will get cancelled, you will get beta belongs to K alpha plus C1 beta. So what does this imply? Since beta is there and you know that alpha plus C1 beta is there, so you can multiply by C1 and you can subtract with this element. So this implies alpha and beta will be there. Right? So this implies this K alpha is strictly contained in K alpha plus C1 beta, because beta is there, so even we don't need to write this. So okay, I should write this. So both of these elements are there in this subfield K alpha plus C1 beta. So this implies K alpha is there, and you know that beta is not there in K alpha. We have assumed this condition, started with that beta is not in K alpha. So this means this is bigger set, strictly bigger than K alpha. This is a strictly bigger subfield. So this will imply this is a contradiction because we have considered this to be maximal in this condition of chain. If we attach one element, if we consider simple subfields, then we have considered this to be maximal. So if this is the condition, then we got a contradiction. So what should happen? This should be equal. This implies L should be equal to K alpha. There should not exist outside it, and that means this is simple. Is that okay?
Okay, ma'am. So once I have to check second case, so where you consider that K of alpha is infinite.
K of
So
alpha,
case
no,
two,
no.
case two.
K is
Yes, sorry.
infinite.
Sorry. K is infinite. So
So I didn't
last part I have understood
get.
whatever you.
So we used alpha, the infiniteness of alpha here. So we considered K to be infinite. Then we considered like simple subfields, like we take Kx where x belongs to L. Then these are all subfields of L which contain K. So that means this set should be finite, because we know that the intermediate fields are just finitely many. So this set should be finite. Now what we can take, we just take a maximal one in some chain. So there could be many chains, there could be many containments. We don't know. There is some, let's say x1, you have K, x2 you have K, and there is some other, let's say K, x3. I'm just picking any representatives. I don't know, K, x5, something like there could be many chains. We don't know, but we just consider the maximal one. We just consider any of this chain, and from any chain we consider the maximal one. And maximal one means there is no other in between, like there is no subfield in between which is of simple type. Like simple type means of the kind K alpha. Like we are not talking about K alpha comma beta, we are not talking about that. We are just saying which looks like simple, like which is a simple field, so simple extension of K. So we consider the maximal one, and then in this terms, like there is no beta such that K alpha is contained in K beta which is contained in L. So alpha beta is again a representative. This next beta is not related to this one, so if you want I can use gamma. Okay, Now we claim that we have picked this maximal one, then L is equal to K alpha. This maximal one, L is equal to exactly equal to this maximal one. So suppose
Achha.
not, we considered beta. Then there will be a beta such that beta belongs to L minus K alpha. Then you consider the sets of some subfields of L which contain K, and we take of the type alpha plus C beta, where C is varying over infinite
As k
field.
is infinite.
Since K is infinite, so C will be infinite. Like how the options for C are infinite. Then since so we cannot have infinitely many subfields again, so there will be some distinct C1 and C2 such that we will get K alpha plus C1 beta is equal to K alpha plus C2 beta. Just pick two.
Ma'am, here k alpha plus c1 beta is I mean k alpha plus c1 beta must be equal to k alpha plus c2 beta for some different c1 and c2, distinct c1 c2. How can I ensure that it must be different for different c1 c2, for different c1 c2, this field must be equal.
So that's what we are saying. This set, what is this set? This set is of like alpha plus. I'm not sure if K is countable also. So this set is just we are varying C over this field K. Okay.
Okay. Yes, yes.
So and K is infinite. So this will have infinitely many elements.
Hmm. Hmm.
Okay, in terms of different C, but we cannot have infinitely many subfields. So as a set there.
As we are given that it must be finite.
Yeah, this set
Uh,
should be finite.
so
So there will be some C1
okay,
and
okay.
C2
I have
distinct
understood.
yeah, distinct C1, even more, but at least there will be two
Okay,
C1 and
okay, okay.
C2. Yeah.
Getting
So
the point.
yeah, so you will get this condition, and then there are two elements, like you know that these two fields are same. So you have this element and this element. Both of these elements are there in, you can pick any representative. We don't care. K alpha plus C1 beta. So these two elements are there, and then we do some trick to get beta actually. So since C1 and C2 are distinct, you can actually get beta here. So you get beta belongs to K alpha plus C1 beta, right?
Hmm.
So now you know that beta is there. Since this element is there, alpha plus C1 beta is there, and you have beta also, so you can just multiply by C1 and subtract it. So you will
Yes, yes.
get alpha also. So alpha and beta both are there. Since
Hmm.
alpha and beta belongs to K C1 alpha plus C1 beta, that means K alpha is there, because alpha is there, K is there. So
Okay, okay, okay.
this one will be there, but this will be strict because beta is not there in K alpha.
Yeah, we have assumed that.
And since this is maximal, it should not happen.
Okay, okay.
Yeah.
A good concept, man.
Yeah.
For that better question.
Great.
Once you have to scroll down the page because I have to take screenshot. I have not written
Oh,
yet.
so I upload the notes also.
Oh,
I write it properly and upload the notes.
yeah, but
Yeah, 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 yeah. You
we have
can.
understand whatever you have read in class. I want to say I have written almost
Okay.
whatever you have worked on.
Okay. Okay.
Last
Great.
last two pages I was busy to understand the
Okay.
what
Okay.
are
Okay.
going.
Sure. 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 So this is the page. I can even, if this helps, I don't know. I can even do this. Yeah. Maybe. Yeah.
Okay. Page
And next
or
page. Yeah.
okay.
Yeah, this was the last. And
Okay,
now,
okay.
okay. So next question is nothing, but I can even give you a hint. So it says, L over K is algebraic is important in your question. Like this is algebraic. It is important in the part B. So if it is not given to be algebraic, then even simple extension need not imply, if L over K is not algebraic, then this need not imply that this has finitely many intermediate fields. Okay, this need not be true. So to give an example, you just take L to be kx. Now x is intermediate. Oh, sorry. So what do we say? Indeterminate. Sorry. So this is a variable. Indeterminate. Yeah. So this is a variable. So and what is a variable? Variable is really, this cannot be algebraic ever. So this extension is never algebraic, not algebraic, right?
Yes.
Because you cannot find a polynomial. So this is not algebraic. That means now so we claim that, so and you know that this is a simple extension because you have just attached one element, so it can be written with the primitive element x. So you have L. So this is a simple extension, but it is not it does not imply that these have finitely many intermediate fields. So what you can take k x raised to power like, so I mean for all m belongs to n, for each maybe. So s, so I mean to say and even I claim that this has cardinality infinity. So infinite means, or maybe I can say, you consider this this will be your, this will at least be, so this set is there in k, sorry not k, this set is there in j l comma k. So you have these so why this is in between? Because kx, between k and kx you have powers, like you can have kx raised to power m, because kx contains x raised to power m, all the multiples of x itself multiple. So you can have all the ways like this. Okay, and now if this is the case and we claim that kx raised to power m is not same as kx raised to power n if m is not equal to n. So k by, yeah, kx raised to power m is not equal to kx raised to power n if m is not equal to n. So this is one condition we are using, because if this is the case, if this is the, if, or maybe why this cannot be the case, if this is equal to kx raised to power n, then what will happen? So let's say m is, without loss of generality, you just say m is less than n, then you can write x raised to power n belongs to this set, right? So that means you can write is it this in terms of sum f x raised to power m upon g x raised to power m, where f and g belongs to kx, ky. So there is some, okay, some other variable just to say. So basically you can write x raised to power m in this term. Okay, so now what you can, and this is non-trivial, and this will imply that there exists some polynomial. So maybe this implies kernel of x, kernel of sorry, epsilon capital X in this field, let's say k x raised to power any field you can take, sorry, or maybe you can just say kx, this is not equal to 0, like there is some non-trivial linear combination where if you put x you will get just 0, because this is a non-trivial linear combination, because you are saying that because m and n are different, so it and m is strictly less than n, so you will always have x raised to power n into some multiplication like g x raised to power m. So this is a non-trivial linear combination. So this will imply that kernel of epsilon x comma in kx, uh, sorry, not in kx, in k, because the coefficients are in k. So you have some, you just assume some powers, and there is x you can put. So kernel is non-trivial. This implies x is algebraic, which is a contradiction. X cannot be algebraic, right? So you have infinitely many subfields. So this is the condition which is true always. So this implies this set is infinite. There are infinitely many subfields, at least these many. So there might be more, we don't care, but at least it is infinite. Is that okay?
मैम
Yeah.
नॉन ट्रिवियल लिनियर कॉम्बिनेशन मतलब तो
हाँ, so
यार यार linear combination मतलब field any element from field into that vector space element summation. So here
so
gx is
okay,
called
okay. Uh,
x to the power n is one kind of
okay,
polynomial.
sorry, not don't say linear in linear combination, I'm sorry. So non-trivial polynomial
Hmm.
in k, okay, in kx maybe. So this is some polynomial where you put, so this will give, so let's say gy y raised to power n minus f y. So this will be some polynomial which will be non-zero.
Non-zero, exactly.
Okay, so yeah, so this polynomial is non-zero.
So kernel
Then
kernel
yeah,
non-trivial.
and when you put x, it will become 0. So x has to be algebraic, but that cannot be true. So that you can give as an explanation. So kx raised to power m can never be equal to kx raised to power m. Yeah. Yeah. Okay.
Oh.
Yeah. So I'll stop here.